Okay, we want to continue with the lecture now, and knowing the three signals, the three types of signals, just help us to understand that signals can be categorized differently, but the question now is how do we get these signals? So we're going to take a look at that, and here is a block diagram that shows that we have a parameter that we want to observe, and from this parameter we have to use a sensor. So we have a sensor here, the parameter, the sensor will observe some characteristic of the device or of the person, or physiological phenomena that we want to measure. And so the sensor converts the biosignal into an electrical signal. Electrical signal is what we can use. Okay. Then once we get the signals typically comes mixed with noise, which means it has other signals that we really don't want. And so we have to do signal conditioning, and the purpose of signal conditioning is actually to amplify the signal more than the noise. So what happens is that if we have a signal and the signal is of a certain amplitude and the noise is of another amplitude, after we amplify, the signal should be very much bigger and the noise level should just be maybe slightly bigger. Hopefully it's the other way, we can actually reject the noise, and this is possible with some amplifier designs. Okay, the next stage after we have finished signal conditioning, we want to digitize it. Why do we want to digitize this? It's quite simple, because nowadays most of the processing is done using a computer or a microcomputer. So we want to have a data acquisition system, and the data acquisition system converts the analog signal into a stream of digital data, and digital data is what the microcontroller will process. And once you have this stream of digital data, you store it in a memory, and you can now write programs, and the programs can process this data and then extract features. And from these features, you can then deduce certain things, certain behaviors about the biosignal that we were observing. So, also digital signal processing can be used to reduce noise further, in addition to extracting out the features that you want. So, a short summary here is that biosignals often have very small amplitudes, and this signal tends to be buried in noise, which means noise is bigger than the signal. And what we really want to do is we want to amplify the desired biosignal, and in order to do this, we use signal conditioning, data acquisition, and digital signal processing. In doing this whole process, we want to faithfully reproduce the signal. We don't want to have distortions that are perceptible. And because perceptible distortions, which means distortions that can be interpreted as a feature, can lead to misinterpretation or misdiagnosis. Okay. So in signal acquisition and processing, the weak signal from the sensor is amplified, so that's just a summary of what I spoke, and this slide just covers that, so I'll just go quickly through it. And so the signal amplitude then becomes stronger than the noise amplitude, and the conditioned signal is then sampled by the data acquisition system. Sampling is performed at a fixed rate to make it easy to reconstruct, and minimum sampling rate to be used must be twice the signal's highest frequency component. Typically we use much higher than that. An analog to signal converter digitizes each sample, and the analog signal is now converted to digital data. The computer can now use the data and perform digital signal processing to reduce the noise further if necessary, or to analyze and extract key information from that digitized signal. To convert analog signal to digital data, we have to decide how often we want to sample the data. If we sample the data very frequently, then we have an excessive stream of data coming in. In other words, we've got a lot of information, of which some of which may not be necessary. On the other hand, if we sample a little too less, we might have other problems. So let's take a look at the problems that we will face. So first, let's take a look at signal oversampling and reconstruction. when we digitize an analog signal to digital data, the proof that we have digitized it correctly is that we should be able to reconstruct back the signal. That means from that stream of digital data, we send it out to a digital to analog converter, and we should see the signal to be the same as the original signal. So let's look at the diagram here. We have here a sinusoid, 1 volt peak, so that's the amplitude, plus 1 volt, minus 1 volt, that's what 1 volt peak means. And the frequency is 1 hertz, so if you look at the time here, we have 1 second time frame, 2 second time frame, 1 hertz means 1 cycle per second, so in 1 second we should have 1 complete cycle. And as you can see from this waveform, it is exactly 1 complete cycle for every second. Now we are sampling at 10 samples per second, which simply means that within 1 cycle, we should see 10 samples. So, and if we were to sample that, then we will see that the first point that we take is at a 0 point. Second point, we see the amplitude, and this amplitude corresponds to this waveform. And so we go on, and we can roughly make out that all the samples here correspond to the shape, or at least their peaks correspond to the shape of the sine wave. And if you were to count that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have here 10 that makes up 1 cycle. So this is 10 samples per second. So every sample is done every 0.1 second, or every 100 milliseconds we are doing 1 sample. When we reconstruct back, all we have to do is just send the sample signals through a low pass filter, and when we do that, we find that we can get back the sine wave. And intuitively you can see from tracing the peaks of the sampled waveform, we can roughly see that it is a sine wave. And when we pass through the low pass filter, it gets restored back to the original sine wave. So that is oversampling of 10 samples per second. You can see quite clearly that it does look like a sine wave. Now what happens, and of course when you reconstruct it, your signal is 1 hertz, which is correct, because you started out with 1 hertz, you should get back 1 hertz. Okay. Now when we do undersampling, in undersampling, that means we are sampling the waveform too slow. What happens when we sample it too slowly? Let's take a look again. Here we have the same signal, sinusoid, 1 volt peak, 1 hertz, and our sampling rate is 1.33 samples per second. So 1.33 samples per second, so this is rather slow. If you look at it, we have 1 sample every, we have 1.33 samples every second. So we should slightly have more than 1 sample per second. Okay, but so every second we expect to have about 1, and occasionally we will see 2, occasionally we will see none. Okay, so this sample at every 0.5 seconds. So in this case, when we look at the peaks that we observe, we find that the peaks seem to imply that there is a sine wave that is much slower than it actually is. And when we pass the sample signal, which is very few, we see that the filter will approximate the waveform to be a sine wave, but the sine wave is actually of a much slower frequency than it actually is. So what happened here? So the reconstructed signal is wrong. We started out with 1 hertz, and we conclude, looking at here 1 cycle, or from half cycle we can reduce, that the frequency is 0.33 hertz. This is obviously wrong. We start with 1 hertz, we should get back 1 hertz. So the error that we get is called aliasing error. So aliasing error is a signal that is generated when we undersample a waveform of a particular frequency. Okay, and so the question now is that if we oversample, we get a very nice signal. What happens if we undersample, we get a wrong signal? Is there a signal frequency that we should sample at? Is there a sampling rate that we should choose in which it will just about work? And there is, and that minimum sampling rate is called Nyquist sampling rate, which we will talk about in a short while.